Look at these excavators dredging this riverbed. They're mining natural sand, and the construction industry is consuming it at a pace the earth can't replenish. Meanwhile, our cities are drowning in a different kind of material. Urban demolition generates billions of tons of waste every year, and roughly half of that is just old, discarded clay bricks. But what if we took that rubble, crushed it down, and used it to replace the sand we're running out of? Engineers call this waste clay brick aggregate, or CBFA. On paper, this sounds terrible. Old clay bricks are structurally weak. They're heavily fractured, riddled with microscopic pores, and absorb water like a sponge. That's a massive problem for plastering mortar, the protective skin applied to the outside of a building. Mortar has to be incredibly resilient and weatherproof. Mixing weak, thirsty garbage into it seems like a guaranteed way to make a wall crumble. Evaluating this mortar addresses a looming supply chain collapse. With natural sand vanishing and landfills hitting capacity, recycling our own urban ruins becomes a matter of industrial survival. To see if this could actually work, researchers systematically replaced the natural river sand and mortar with crushed bricks, testing batches at intervals from 30 to 60%. This chart tracks the compressive strength of those mixes over 28 days. The data shows that right here, at the 30% replacement level, the mortar actually became noticeably stronger than the traditional sand-only mix. This next graph measures tensile bond strength, the mortar's ability to actually stick to a wall without peeling off. Once again, performance distinctly peaks at that exact same 30% ratio. To understand why, we have to look closely at those seemingly terrible physical traits. Because the crushed brick is incredibly porous, it acts exactly like a microscopic sponge, pulling in excess water. This improves the mortar's overall water retention, keeping the wet mix from separating. Natural sand is smooth, so cement struggles to grip it, but crushed brick has jagged edges that physically interlock with the cement like a puzzle. Plus, brick dust reacts chemically, generating microscopic crystals that grow and fill the empty voids. The very things that made crushed brick seem like a terrible building material, its cavernous porosity and fractured, jagged surface, are exactly what make it structurally superior at the microscopic level. If replacing 30% of the sand makes the wall stronger, the obvious question is, why not push it further? Look at this graph showing the water requirement. As crushed brick climbs past 30%, that sponge effect becomes a massive liability. It absorbs so much moisture that the mixture requires a steep, continuous increase in water to remain workable. And this chart reveals the consequence of that extreme absorption. As the replacement level hits 50 and 60%, the setting time of the mortar steeply drops off, meaning the wet mix thickens way too fast for anyone to actually use. By the time the mix hits 60% replacement, it officially fails national building standards. The mortar loses its consistency rapidly, and as all that excess trapped water eventually evaporates, the material shrinks and cracks. This is the reality of materials engineering. It's an optimization puzzle. The goal is to find the exact mathematical threshold where we maximize environmental sustainability without crossing the line into structural failure. After running the numbers, the researchers arrived at a definitive limit. The optimal replacement ratio for this sustainable mortar is exactly 50%. At that 50% threshold, the mortar passes every rigorous legal requirement of national dry mixed plastering standards, holding its required compressive strength and structural workability. Adopting this specific ratio across the entire construction industry would instantly cut our reliance on increasingly scarce natural river sand in half. It also provides a massive secondary benefit. Instead of hauling urban rubble out to landfills in heavy, gas-guzzling trucks, we can consume that waste locally. What used to be an expensive disposal liability becomes a highly economical green building material. Achieving true sustainability in the 21st century means we have to stop relying purely on extracting new resources from the earth. Instead, we can intelligently re-engineer the discarded rubble of our past, transforming it into the resilient